Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. Okay, so now you can recall that in the last lecture we had initiated a discussion on different types of probability mass functions, and we had considered the discrete uniform distribution, right. So, now in this lecture we are going to consider some more probability mass functions, and basically we are going to consider the Bernoulli distribution and binomial distribution. So, the first question comes under what type of conditions these two probability functions are going to generate the probability, or I can say under what type of condition you can use these probability mass functions to compute the probabilities and different types of properties of the data. So, now you can recall that in the last lecture we started with degenerate distribution. So, in the degenerate distribution there is only one point at which the probability is concentrated. Now, I will try to extend it, and I will try to consider that suppose the probability is concentrated at two different points. Now, as soon as I make this statistical statement, you get badly confused that what is the meaning of this, and this is going to happen in the entire course. But my suggestion to you is that try to think carefully what I am trying to say. I am simply trying to say that the probability is concentrated at two different points, only 2 points. Now, can you think that is there any practical condition or practical situation where such a phenomena can happen? Right. There are numerous examples, not one, not two. For example, if I say whenever somebody is appearing in an examination, there are only two possibilities, success or failure. And definitely success and failures have some associated probability. One can always say that okay, there are 70% chances that the student will pass the examination, and there are 30% chances, obviously 30% will come as 100 minus 70%. So, 30% chances are there that the student may not succeed in the examination, right. Suppose if you want to know whether it will rain today or not, you can say okay, there are 80% chance that it may rain today. So, obviously, there are 20% chance that it may not rain today. So, in all these cases, if you try to see, the probabilities are concentrated only at two different points. So, you can see it is pretty simple. The only thing is this, you have to develop a statistical thinking, how to think statistically. So, now in this case I will say simply that we can use the Bernoulli distribution. And similarly, in case if you try to repeat this experiment for a certain number of times, then this Bernoulli distribution will help us in getting a binomial distribution. That will also be used under some special type of conditions. Well, what are those conditions? That is what we have to learn here. So, one thing I would say that whenever I am trying to initiate a discussion on any probability mass function or say any probability density function, try to divide your thought process into two parts. One is theoretical and second is application oriented, that where it can happen. Although I am trying my best to take couple of examples in every probability functions, so that I can convince you that these things are going to really happen in practice. And yeah, I will also try to show you that the same probabilities that you are computing theoretically using the probability mass functions how they can be computed in the R software directly. Well, those things will start now. Right. So, let us begin our lecture, and first we try to understand the Bernoulli distribution. Okay. So, now as I said, the degenerate distribution indicates that there is only one possible fixed outcome, and therefore, there is no randomness involved in it. And it follows that we need at least two different possible outcomes to have randomness, right. Means at least you should have two different outcomes in which the probabilities can be divided, otherwise there is no variation, right. In all those events, like as sun will rise in the east direction, it will always happen, there is no randomness. So, we need at least two values, so that we can incorporate the uncertainty in the observations. Now, after this thing, we have to understand what type of mathematical functions can be used that can illustrate this type of phenomena. So, now I try to introduce here the Bernoulli experiment. This Bernoulli experiment is a random experiment in which the outcome of the experiment can be classified in one of the two mutually exclusive and exhaustive ways, like as success or failure, male or female, life or death, defective, non-defective, etc. So, this Bernoulli experiments will give us an idea about the Bernoulli distribution. So, a Bernoulli distribution is useful when there are only two possible outcomes, and our interest lies in any of the two outcomes, right. For example, there is a success or there is a failure, whether a customer buys a certain product or not, right. There is success or failure, or the newly born baby is male or female. The name of this Bernoulli distribution is after the Swiss mathematician James Bernoulli, right, just for your information. And in general, these outcomes are usually indicated by the values 0 and 1. Well, we already have seen that whatever are the outcome that we are getting, they have to be converted into some numerical value, and that is what we had discussed when we initiated the discussion on the random variable. So, suppose that there is a trial, there is an experiment whose outcome can be classified as either as a success or a failure. So, for example, now success can be given the value 1, failure can be given the value 0, or even vice versa also, right. So, now in case if we assume that x equal to 1, there is a random variable x which takes value when 1 when the outcome is a success, and the random variable x takes value 0 when the outcome is a failure. One thing I would say once again, that it is not necessary always to take x equal to 1 as success and 0 as failure. You can also take x equal to 0 as success and x equal to 1 as failure. It depends on you how do you try to define the this random variable and the associated values, but means psychologically it is more easy to understand that x equal to 1 is indicating the success, right. So, in this case, the random variable x has a Bernoulli distribution if the probability mass function of x is given by this mathematical function. And if you try to say, this is a very simple thing, you are trying to say that probability that x equal to x when x equal to 1, that is success, it takes the value p, which is the probability of success, right. So, p is the probability of success, and in case if x equal to 0, then we know that the probability of success plus probability of failure, it is equal to 1, because both these events are disjoint. So, this probability that x equal to 0 will simply be 1 minus p. And yeah, although I am not giving you here the proof, but the cumulative distribution function in such a case is given by this function here, capital F x, which is equal to 0. If x is less than 0, it takes value 1 minus p if x is lying between 0 and 1, and it takes value 1 if x is less than or equal to 1, right. And in case if you try to find out the mean and variance of Bernoulli random variable, then expected value of x will come out to be p and variance of x will come out to be p into 1 minus p, right. There is no issue. Well, yeah, means you can ask me at this stage that this p and that is the probability of success, how it is going to be known to us. So, yeah, in practice it is unknown to us, and then we have different ways to estimate it on the basis of a random sample that we are going to discuss in the forthcoming lectures. Now, let me try to take a very simple example to give you some idea that under what type of condition these types of probabilities can be used. So, suppose there are 300 lottery tickets and 50 of them are marked as winning ticket. That means, if anybody gets one ticket out of those 50 tickets, it will be a win, right. So, suppose we define an event A as ticket wins, and this is coded as x equal to 1. That means, x equal to 1 is going to indicate that the ticket is coming from these 50 winning tickets, and the probability is p of having a winning ticket before any lottery ticket has been drawn, right. Means somebody has to buy the ticket before the draw. So, in this case, if somebody wants to compute the probability of winning the lottery or probability of losing the lottery, that can be obtained as probability of x equal to 1, which is the probability of success, probability of getting a winning ticket, that will be 50 upon 300. That will be 1 upon 6, and this 1 upon 6 is actually here p. And the probability of failure, that means the probability of getting a ticket which does not win, that will be probability x equal to 0, that will be 300 minus 50, which is 250 divided by 300, and this will be 5 upon 6, which is actually the value of 1 minus p, right. So, the mean and variance in such a case will be given by expected value of x is equal to p, which is equal to here 1 upon 6, and variance of x is going to be p into 1 minus p, which is 1 upon 6 into 5 by 6, which is 5 by 36. So, this is how you can characterize the entire phenomena once you have got the probability of success and the average value variability. Possibly you will get a fair idea about that phenomena, right. Now, how these things can be done in the R software, and yeah, means these probabilities you do not have to compute manually, but how to get them in R software, this I will try to explain you after I consider the binomial distribution, because this Bernoulli and binomial, they are very closely related. So, now we consider the binomial distribution, and suppose a coin is tossed, and suppose the first toss results in head. Now, what will happen to the second toss? The second toss has two possible outcomes, head and tail. Now, what is going to be the outcome, that you do not know unless and until the experiment is completed. And in this case, if you try to see one very important characteristic, that the outcome of the second toss does not depend upon the outcome of the first toss. And the same story is going to continue if you try to continue to toss the coin. The outcomes of a given toss do not depend on the outcomes of the earlier tosses, right. So, in general I can say that the result of one toss does not depend upon other tosses. So, suppose now we try to consider an experiment and we try to define the random variables which are going to ultimately give you an idea about the binomial distribution, or what type of probabilities can be considered under the binomial distribution. So, consider the following random experiment and the random variables. Say, for example, in the next 20 births at a hospital, we want to know what is the number of female birth, that how many girls are born, and let this number be actually here x. So, if you try to see whenever a baby is born, there are two possibilities. Either the baby is a boy or a girl. So that means, don't you think that it is looking like that that every outcome is following a Bernoulli distribution? It has only two possible outcomes. And suppose if I take one more example, that a machine produces 1% defective parts. So suppose capital X is the random variable which is indicating that number of defective parts in the next 25 parts produced. So every time in both the cases, the outcome is going to be governed by the Bernoulli distribution or the Bernoulli trials. So all the outcomes are the Bernoulli trials, and if you try to see, we are interested here in a certain number of the occurrence or non-occurrence of the events, right. And in case if I try to convince you and I try to take two more examples, suppose any sample of air has a 10% chance of containing a particular type of rare molecule. So now let X be the number of air samples that contain the rare molecule in the next 18 analyzed samples, right. So once again means you can see the molecule is absent or present, so that is a sort of Bernoulli trial, and then you are interested in the number of times the event is occurring. And similarly, in a multiple choice test, suppose it contains 10 questions, and each question has 4 alternatives, 4 choices, and you have to guess each question. You don't know the answer of any of the question. Then in every question there are 2 possibilities, whether your answer is correct or incorrect, right. So in case if you consider here a random variable, the number of questions that are answered correctly, then you are trying to find out the probability of certain event that has occurred. So in all these cases you can see that you are trying to repeat the Bernoulli trials, right. So now we try to extend it and we try to make it more general, and we try to consider a small n number of independent trials or repetitions of a Bernoulli experiment with probability of success p in each trial. So obviously this probability p remains constant in each of the trial, right. So now this depends on the objective of the experiment, that in each trial or repetition we can observe either the event A or the event A complement. For example, either we are interested in the outcome of the newly born babies are male or its complement is female. In case if you are interested in the number of successes, then its complement is going to be the number of failures, right. So at the end of the experiment we have thus observed A between 0 and small n times, because every event is resulting into 0 and 1, and you are trying to repeat the experiment a small n number of times. So there will be something like 0, 1, 1, 1 and so on, but the maximum number of times one can occur in all the trials will be that every trial is having only 1. So this number is going to be small n. And suppose we are interested in the probability of A occurring k number of times, then in under such type of cases the binomial distribution is used, right. For example, if you try to take here means any example, right. In this example also there are 10 possible questions. So the success and failure can be say indicated by 0 and say 1, and at the most what will happen that no solution is correct. So x is going to take the value 0, and if all the solutions are correct, then x is going to take the value say 10. So that is what I was trying to explain you here, right. So now suppose a coin is tossed suppose 10 times, and the event of interest here is the number of heads. So the random variable in this case is going to be number of heads in the 10 experiment, and x is going to take the possible values as say k equal to 0, 1, 2 up to here 10. And now suppose we want to know the probability that a head occurs in 7 out of 10 trials, or say in 5 out of 10 trials. So under this type of condition we can use the binomial distribution to compute the probabilities, and we assume that the order in which the heads or the tails appear is not of interest, only the total number of heads is of interest. So we are not bothered that what is the individual outcome, whether success or failure, but we are interested only in the number, right. So you can see here the outcome of these types of trial is actually a sequence of Bernoulli trials, and the outcome is going to look like as a n tuple of zeros and 1, like a 0, 0, 1, 0, 1 up to here n times. Then the next that can be say 1, 1, 0, 0 and so on, right. So out of these small n number of trials, means if you say that there are small x successes, that means x is going to take the value say 0, 1, 2 up to here n, right. And depending on the success, the remaining say n minus x events will indicate the complement or the failure. So obviously now you can see the total number of ways of collecting x successes in n trials is going to be n choose x, obviously that we already have done. Now the trials are independent and the probabilities of success are here is small p, and the probability of failure here is 1 minus p, that we are trying to indicate by here small q. So because all these events are independent, so you know that if there are two events A and B which are independent, then probability of A intersection B is probability of A into probability of B, right. So the probability of each of these ways will simply be here p raised to the power of here x into 1 minus p raised to the power of here n minus x. So this is indicating there are x times successes, so it will go p x times and multiplied by say n minus x failure. So 1 minus p up to here n minus x times, right. So now in case if I try to find out the total probability, that will give us the probability mass function of x, that is going to be sum of probabilities of n choose x mutually exclusive events. And if you try to sum this p raised to the power of x into 1 minus p raised to the power of n minus x n choose x time, you get here a function like n choose x p raised to the power of here x 1 minus p raised to the power of n minus x, and this 1 minus p can be replaced by here q, right. So now I can say the probability that the random variable x takes the value k, where k is equal to 0, 1 up to here n can therefore be calculated as probability that x equal to k is equal to n choose k p raised to the power of k into 1 minus p raised to the power of n minus k, or that can also be written by replacing the 1 minus p by q. So if you try to see what I have done, I have just considered a particular type of probability, and I have illustrated here how you can compute the probability, and ultimately you have now converted, you can see here in the last part you have converted into a very general statement how to compute the probability. And now I can just say that this is going to generate the probabilities of these types of events in which you are interested in finding out the probability of success or failure out of the number of trials where the trials are going to be Bernoulli trials. So in this case, because this was because at this moment we are beginning, so I have given you here the complete idea that this probability mass function or equivalently the probability density function, they are not coming from the sky. We are simply trying to compute the probability of certain type of events, and finally we are trying to write them in a nice mathematical form which can be used directly without any problem, right? Because I personally feel that sometimes I see that students are confused that how the probability functions are coming into picture, and they say that okay, there are so many probability function and how are they going to know that where to use, how to use, when to use, etc. So that is what I am trying to cover in the beginning, and as soon as we feel that we all are now matured enough, I will try to reduce the discussion. Right. After that, as soon as I say that okay, let there be a random variable which is following this probability mass function, you can very well assume that this is coming from some through proper methodology, proper concepts, although I may not be able to give you the complete proof or derivation of all the probability mass function or the probability density function. So that is why in this case I have given you a detailed information, but it may not be possible for me every time to give you such detailed information. But if you want, you can simply pick up a book and then try to understand them. So now I can define the binomial probability mass function. So a discrete random variable x is said to follow a binomial distribution with parameters small n and small p if its probability mass function is given by probability of x equal to k, which is equal to n choose k p raised to the power of k into 1 minus p raised to the power of n minus k, when k takes the value 0, 1, 2 up to n and 0 otherwise, right. And if you want to use here 1 minus p here as a q, you can simply replace it. And we indicate symbolically that x follows a binomial distribution with the parameters n and p by writing this x equivalence b and inside the parenthesis small n comma small p. So that is a standard language, standard symbolic language in which we try to represent this thing. And if you try to take here n equal to here 1, what do you get? If I write down here x binomial is 1 p, don't you think that you are going to get here the Bernoulli distribution? Think about it. Answer is yes. So in the case of binomial distribution, the mean of x can be found to be as small n into small p, and the variance of x can be found as small n p into 1 minus p, or we write down here say n p q. So the mean here is n p and variance here is n p q, right. And you can see here that p and q, they are always going to lie between 0 and 1. So you can see here in this case mean is greater than variance, right. So and if you want to have the results for the Bernoulli distribution, you can simply substitute here n equal to 1, and a Bernoulli random variable is therefore binomial 1p distributed, and that is the thing that we are going to use in the software also, right. So can we try to take here an example and try to show you, and the same thing I will try to do in the R software also. So suppose there is a coin which is unfair, means the probability of head and tail are not exactly the same, but suppose the probability of tail is 0.7, and suppose the coin is tossed 3 times. So now the outcomes of the tail are going to be indicated by 1 and the outcome of heads are going to be indicated by 0. So now the unfair coin is tossed 3 times. So we try to define here the random variable as the number of tails in each trial. So following are the outcomes. Why? Because the coin is tossed 3 times. So every time you can have a different types of outcomes. So here I am trying to illustrate all possible outcomes, which are actually 2 cube, that is 8. So you can get here tail, 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 that you are trying to indicate by 1, 1, 0. You are getting tail, tail and head, that is being indicated by 1, 1, 0. And similarly, I try to write down here all the possible outcomes, right. And then I try to define here the value of capital X. So in this case, the number of the tails are 3. So this value comes out to be here 3. In the second case, there are 2 tails. So this capital x takes the value say 2 and so on. So, these are the values of the number of tails that can be obtained in every trial, right. And now, let me try to give you some details of this computation. For example, if you can see here in the first outcome there are 3 possible tails, right, there are 3 tails. So, this number 111 is obtained by the computation 3 choose 3, that is leading to x equal to 3, right. You are not observing it, but you are trying to say that in the 3 trials there are 3 tails. Now, similarly, if you try to look at here, here and here, in these cases what is happening, that the total number of cases in which you can obtain 2 tails in a sequence of 3 trials, that can be obtained by say 3 choose 2, and that is leading to x equal to 2. And similarly, in these 3 trials, see here 1 0 0 0 1 0 0 0 1, the values here are 1. So, in these 3 cases the total number of tails in the 3 possible trials, they are obtained by 3 choose 1, and that is leading to x equal to 1. And similarly, in the last outcome say 0 0 0, means you are trying to obtain the 0 number of tails in the 3 trials, and that leads to x equal to 0, right. So, now in this case, if you want to compute the probability, for example x equal to 2, that can be simply obtained by 3 choose 2 into the probability of getting a tail which is 0.7 into 1 minus 0.7 n minus x. So, n here is 3 and x here is 2, and this can be computed as 0.441, and the mean is going to be 3 into p, that is 3 into 0.7, 2.1, and the variance is going to be 3 into 0.7 into 0.3, which is 0.63. Well, I have taken this example and I have computed it here mathematically to convince you how these values are obtained, and I will try to do the same thing in the R console also, right. But before I leave, let me try to give some important results. So, one important result in the binomial distribution is that if there are 2 stochastically independent variable x and y, and suppose both are following a binomial distribution. So, x is following a binomial distribution with parameters small n and small p, and y is following small m and small p. So, the probability in both the random variable remain the same as p, but only the numbers m and n are different. In this case, if you want to find out the distribution of x plus y, that is going to be a new random variable, then the x plus y will have a binomial distribution whose parameters will be n plus m, and the probability will remain the same as p. So, this is actually the additive property, and this describes the additive combination of 2 independent binomial experiment with n m number of trials with equal probability say p, right, and this can be extended also. And if you try to see, this is not really difficult to understand, although there are rigorous proof, but here you can also see that these results can be viewed as follows. For example, every binomial experiment is a series of independent Bernoulli experiments, and this is equivalent to a series of n plus m independent Bernoulli trials with constant success probability p, which in turn is equivalent to a binomial distribution with n plus m trials, right. So, in this case you have a smaller number of Bernoulli trials, that is giving you binomial. In the case of y, there are a small m number of Bernoulli trials that are giving you binomial, and if you can consider that instead of n or m you have n plus m number of Bernoulli trials with the probability of occurrence as p that remain constant in all the trials, then you will have a binomial m plus n and trials and probability as p, Right. So now we come to an end to this lecture, and you can see here I have tried my best to give you the detailed development of the Bernoulli and binomial distribution, and I also try to give you some examples so that I can show you that under what type of condition they can be used. And there are some statistical properties also. There is a long list, but I have just given you here one statistical property, and actually this is useful in data sciences. So in fact, in every probability function there will be lots of statistical properties of those distribution, but I will try to give you here only those properties which I personally feel that they are going to be useful when you are trying to deal with data science and you are trying to handle the problems in the data science, and they are useful from the computational point of view. For example, in this case you can see that if you have got two experiments which have been conducted at two different places, but you see that okay, both are going to follow the binomial distribution, and the only thing is this, their number of trials are differing, but the probability of success is the same at both the places. For example, if you try to see the probability of getting ahead in say New Delhi and probability of getting ahead in say Mumbai, they are the same. So somebody has made say this 20 observation in Delhi and 40 observation in Mumbai. You can club it together, and the new random variable will follow the binomial distribution with say the n is equal to 20 plus 40, that is 60, and with the same probability of success p. So this is what I want, and this is what exactly is in my mind while I am trying to prepare these slides and giving you the lecture. Right, after some time it may change, I do not know, but this is what I have done. So now this is your turn. I will say simply try to pick up a book and try to read the chapter on Bernoulli and binomial distributions. You will see there are many more things, and for me it is not possible to cover each and everything, but the more you learn, the better you are. So you try to take some exercises from the assignment, from the book, and try to solve them. The main thing is this: you have to understand why are you trying to employ here the binomial distribution or Bernoulli? Why not Poisson, geometric, etc., that we are going to discuss in the later lectures, and that will help you using these tools in the real applications. By looking at the nature of the data, you can have a fair idea that what type of probability mass function or probability function has to be used so that you can compute the probabilities correctly. Once you can compute the probabilities correctly, you have solved the problem. So you try to practice it, and I will see you in the next lecture. Till then, goodbye.